Hello, everybody. In this video, we're going to start kind of the technical part of this chapter, which is about Turing machines. And there will be here some repetition of materials that have been studied in CS 103, but there will be a few insights that I encourage you to pay attention to. So a Turing machine, just like a finite automata, as a finite state control. But in addition, it has this infinite read-write tape. We will assume that the tape is infinite on one direction, so it has an end on one direction and then continues on the left and then continues to infinity on the right. And we also assume that the way this machine gets its input is by having the input written on the leftmost cells from the first tape. We will from the first tape cell. We will also make this assumption that whenever the machine tries to go to the left, it stays put, but on the other end, the machine can go to the right. So given the input, the machine does its computation, goes to the left, goes to the right, and at the end, it needs to write the output on the same tape. The output here could be a single symbol, or perhaps accepting or rejecting, but it can also be something else. So okay. That's the paper that introduces Turing machines. And it has some argument why this notion of Turing machines is universal, why it captures computation. And there is a link to this paper from our webpage. I'd say that Turing machines have tried to, in some sense, imitate how people compute, how human computers compute. And kind of imagining that our brain is this finite state control. It has a large control, but it is still finite. And now we can also use additional information, for example, a sheet of paper. And whatever we do on this sheet of paper, we look at a particular location, we read what's there, we can write something, and then we can move our eyes to some other location. And this would kind of suggest this two-dimensional tape, and which would have been fine, but it turns out that you don't need a two-dimensional tape. You can simulate the two dimensions with a single-dimensional tape. So that's, in a sense, a little bit of how this notion captures this human computation. And this is a good place to discuss how theory of computer science, how the foundation of computer science formalizes things, abstract questions, abstract models. So if you look at the Turing machine and you think, oh, this is an abstraction of how individuals, our humans, are doing computations. And imagine that you would go with this abstraction to a neuroscientist and say, you know, I have an idea, I know how to formalize computations. And you tell them this, then they would throw you out of the room because they'll say, okay, you abstracted away the most important aspect. So what happens in this finite control, which is the brain? And they would be absolutely in their right to be upset. But as the theory of computing showed, this very, very, very naive notion of computation has been extremely powerful. And what we've been able to show, and partly you'll see it in this course, partly you won't, influenced by this amazingly simplified definition, is kind of striking. So there is a point in very simple definitions even if they abstract away things that are important, they still let you understand things that are important as well. So let's compare Turing machines and DFAs. Turing machines can do something that DFAs cannot do, which is to both write and read from the tape. So you can imagine that finite automata just as a tape, but it can just read from it. And the head can move left and right. That by itself, if we added to DFA the ability to move the head to left and right, would not necessarily make a big difference, and you will discuss it in one of the problem sets. And in addition, the input doesn't need to be read entirely. So you can decide at any given point, you can decide to accept or reject a string, or you can perhaps not stop at all. And we all know from programming that this is a fear. The fear is that your computation will get into infinite loop. So now, instead of waiting till the end and seeing if you accept or reject, you can accept or reject at any given point. So these are the differences. A priori, they may not have been so dramatic, but as we'll see, they have a dramatic impact on the power of computation. So we can still define and characterize a Turing machine as a graph, just like we did with the DFA, and with a little bit more labeling on the edges of the graph. So the nodes would still capture the different states. And given that you're in a state and you read a particular symbol, you will have a transition labeled on this edge that says what you're going to write and whether you're going to move the head to the right or to the left. So for every state, and given anything that you read, you need to tell me what are you going to do. And what are you going to do is whether you're moving to the right or to the left. So what language is captured here? The language that is captured here is decided is the language that contains 0. And let's see what happens. So only the string that is composed by a single 0. Because when you read 0, you move here. And now if you see the empty cell, meaning that the input is ended, then you're going to move to accept and immediately accept. And if you see another 0, and we assumed here that the alphabet is only the zeros. So if you see another 0, you move into reject. And if you see no 0 at the beginning, so you immediately see an empty cell, you also go to reject. But specifically on the string that contains a single 0, you are accepting. And on all other strings, you're going to explicitly reject. This is why we say that the Turing machine decides the language. It really decides for every string, is it accept or reject. There is another option. Let's assume that this state that was explicitly rejecting would be replaced with another state that is a sink. You cannot get out of it. So given that you're here, you would not accept. But it's kind of a loop. From now on, you're just going to continue reading bits and reading symbols and moving your head, but you'll never stop and accept or reject. So what's the language that is computed? In some sense, it's the same language, because the only string that would reach accept is a string with a single 0. This is the only path for acceptance. But on the other hand, there are strings that cause you not to accept nor to reject. we call such a Turing machine, we will say that such a Turing machine recognizes the language that contains a single zero. So it doesn't decide. It's not that for every input it either accepts or rejects, but it recognizes whenever it sees a string in the language, it recognizes that it is supposed to accept it. But for other strings, it may accept it may reject or may loop. You're never going to accept a string that is supposed to be rejected, a string outside of the language, but you may loop. So this is a big distinction. We'll talk about it a lot in the class between deciding and recognizing. So let's see what Turing machines can do, and let's start with something that Turing machines can do and finite automata cannot do. So a Turing machine can decide, which is the stronger sense, the language composed of W sharp W. So the languages, which is essentially the concatenation of two words that are the same. How would we do it? We can write down this big state machine, but it will be very big. And instead what we'll do here, and what we'll do in most of these classes, use this notion of a pseudocode. So something that's slightly less formal, but gives you a better sense of what's the operation. And you can imagine any language, any programming language that you use here. But of course, you don't get into all the nitty-gritty details of a programming language. So how would you do that? So first, you can search for the number of sharps. If there is no sharp on the tape or more than one, you reject. So this is a procedure that you need. Again, this is even not the entire pseudocode, it's kind of hinted. So here you need to say, okay, you go from the left to the right and you kind of count how many sharps you see until you get to the empty cells. Then you're going to have a loop, which continues as follows. While there is any bit to the left of the sharp, you're going to replace the first bit with this new symbol X and check if the first bit on the right of the sharp is also the same one. If you find that they are not the same one, the first bit on the left and the first bit to the right of the sharp are not the same, you're going to reject. Otherwise, you're replacing both of them with an X. In a sense, you're erasing them. Then if you reach the situation when there is no more bits to the left of the sharp, then by now there should also not be any bit on the right of the sharp. So when you finish the loop, there is no bit to the left of the sharp, and you check if there is anything on the right. If there is nothing on the right, you're going to accept. If there is something, you're going to reject. Let's look a little bit of how this operation would work. And this would require us to do something in addition, some other technicality. In a sense, I'm showing here that to fully formalize a Turing machine, even for something that simple, requires some effort. Which is the reason that we are going to focus on pseudocodes. So at the beginning, you have the state, you have your input. So here the input is 011 sharp 011, which should be accepted, right? It is in the language. What you're going to do first is going to look for the sharp. And in addition, this is where you're verifying that there is a single sharp. In addition, what you're going to do is move the entire input to the right. So here you're still looking for it. And now you're you found the sharp, so now you're looking to find the empty cell. You're looking to find the end, and if you find another sharp in the middle, you're going to reject. So now, and every time you kind of remember within the state, what is the what are you supposed to write on the cell when you're copying it? So now you found both the sharp, the empty cell, and you're moving to a new state that tells you to go left. Now you're going left all the way until you are in an empty cell. Why did we do that? Why did we copy the entire input to the right? We did it because of this assumption that when you move to the left and there is nothing more to your left, you're going to just stay put. So let's say the last one, the last bit is 0, and you move to the left. You can distinguish, and you just stay put and see a 0. So you can distinguish if you just saw 2 zeros or the same 0. So we prefer our input to be a little bit kind of to have it between two empty cells. This is the kind of level that we would not bother us most of the class, but this is the first thing we're doing in Turing machine, so we want to do that. Of course, there is a different model of Turing machines when the tape is unbounded in both directions, and there this would be a little bit different. You wouldn't need to worry about that. Okay, so we finished implementing 1, and now we need to implement 2. So we look and we found that the first bit is 0. We replace it with an X, and now we're searching for the sharp and for the first bit after it. And we see that it is indeed 0. So we're happy, we're replacing it with an X, and we go left. We find the last X, we go with it to the right. We identify that the first bit is 1. And now we will go to the right, see the first sharp after the X, and see that it's the first bit after the X, and see that it's 1, and replace it 2 with an X. And when we'll continue and finish, we'll reach the fact that there is no more bits to the left of the sharp, and we'll verify that at that point there is no bit to the right of the sharp, and we're going to accept. So that's how this would work, and you can see that formalizing, even in the few things we did, at some point I got too tired to write all the states that are needed to implement each one of these subroutines. And this shows that completely specifying a Turing machine with all the states and all the transitions is hard, and this is why we are going to focus on using pseudocode. Nevertheless, we want to formally define a Turing machine, and one reason we want to do it is to know that it can be formalized. To have, whenever we do something that's informal, it's good to have in the back of our head what is the formal equivalent of it. If somebody forced us to sit down and write things formally, we need to be able to do that. So what are the ingredients of this 7 tuple, which is 7 is bigger than 5, so it's a more sophisticated things than a DFA. So first we have Q, which is still a finite set of states. Sigma is the alphabet, the input alphabet, and it's important that this special symbol, which is the empty cell, is not part of the alphabet. So the Turing machine needs to see that what's written here is not an input, but rather an empty cell. And now we have gamma, which is the tape alphabet. In the tape alphabet, what we know is that the empty cell is part of the tape alphabet because we need to write it there. There should be empty cells. The input is not there it's not infinite. And the entire sigma is part of the alphabet, of the tape alphabet. So the tape alphabet is larger. It contains all of the input alphabet and at least one more symbol, which is the empty cell. There could be more than that. In addition, we have a transition function, just like we had with the DFA, but now it has more to define. So the transition now depends on your state, the current symbol that you've been reading, and what it needs to output is the new state, the new symbol that you are writing instead of the symbol that you have been seeing, and a binary decision whether to go to the left or to the right. So this is the transition function. We still have a start state, Q0. We have an accept state, QAccept. And here we need a reject state, which is explicit. So in DFAs, rejection was just by default. Whenever you didn't accept, you rejected. But in Turing machines, you can run forever. So how would we know that we are rejecting rather than we are still trying to accept? So if you want to reject, you need to explicitly reject by going into the state QReject. Still, a notation, an important notation is a Turing machine configuration. A configuration of the Turing machine contains all the information about its current situation. So you can think about a computer that's going to go to sleep, and it's dumping all of its information into the tape. And now when it will read it again, it can start over as if nothing happened. So what is the information you need to continue simulating a Turing machine? What is the configuration? The configuration is the state, the internal state of the machine, the location of the read-write tape, the location within the tape which we are pointing. This is called the head of the Turing machine. Where is it pointing to? And the content of the tape, at least the finite content that contains symbols. And now we need to encode all of that. There is plenty of ways to encode it. It doesn't really matter. We are going to define a particular way to encode it. Essentially, we're writing the content of the tape, but we're interrupting it with the state. And we put the state just to the right of the location that we are pointing to. So we have here the content of the tape. We have here the state of the machine. And by placing the state in the right place, we are also encoding the position of the read-write head. So this machine is in state Q7. This is the content of its tape. And the read-write is looking at this second zero out of this segment of 3 zeros. Okay, so with this notion of a configuration, we can define what does it mean for a Turing machine to accept, what does it mean for a Turing machine to reject. So we'll start by defining a relation between two configurations. So if we have a configuration C1 and C2 of a Turing machine M, we will define that C1 yields C2 if M, when it's in configuration C1, will move to configuration C2 in one step. So from C1, in one step, you're moving to C2 by the operation of M. If you start M at C1, you're going to move to C2. And to give you an example, if there is this transition, delta of Q1b goes to Q2, the state is turning to Q2, you write C and you move to the left, then the configuration here on the left, AA Q1BB, yields A Q2A CB, because you see that the head is pointing at a B, and the machine is in state Q1. It means that it's going to move to Q2 and move to the left and write C. So it's writing C instead of this B. Here you see CB at the end instead of BB, and it's moving one to the left. Another example, if from Q1 on A, you move to Q2, write C and move to the right, then when you're here, meaning that the machine is in Q1 looking at A, and A is the last symbol, then what you're going to do is replace this A with a C, and you're going to move to the right. So now Q2 is pointing at an empty cell. So to be explicit, we are going to add the empty cell here. Q2 is pointing to the empty cell just to the right of the entire sequence. And now we can say that if W is a string and M is a Turing machine, then M accepts W if there is a sequence of configurations, C0 up to Ck, such that C0 is just the initial configuration. So initial configuration means that you're in the start state, Q0. You're pointing to the leftmost symbol in W, and then you have W written on the tape. So that's Q0 W. Ci yields Ci plus 1. So from this configuration, you're going to move from C0, you're going to move to C1, from C1 to C2, and so on. This holds for I equals 0 to k minus 1. And finally, Ck contains the accept state, Q accept. So somewhere within this configuration, you see Q accept, meaning that the Turing machine has accepted. And now we can define what it is for a Turing machine M to recognize language L. And this is if it accepts exactly those strings in L. For every string in L, Turing machine M is going to accept it. For every other string, it's not going to accept it. Doesn't necessarily mean that it's going to reject it, but it's not going to accept it. We're going to say that Turing machine M decides a language L if M accepts all strings in L and rejects all strings that are not in L. And again, this means that we can define languages to be recognizable if some Turing machine recognizes it. And I want to add this other language, other notation that replaces recognizability. Instead of saying that L is recognizable, we can say that L is recursively enumerable. This is just something you may encounter in books. And if and L is decidable if some Turing machine decides it. And this, instead of decidable, we can also say that it is recursive. It's either recursive or recursively enumerable. So this is pictorially the difference between deciding and recognizing. Deciding means that for every input, you're going to, in some sense, ask if W is in the language or not. If it's yes, if it is in the language, you're going to accept it. If it's no, you're going to reject it. And this means that you are deciding it. For recognizability, what you can do is to say yes, to accept every W in L, and then to reject or loop for every W that's not in L. And we'll see examples where you cannot really decide, but you can recognize. So let's see another example, a Turing machine for deciding. So this is on the easier side, deciding the language that contains all the strings of zeros that have a perfect power of 2 of zeros. So 0 to the 2 to the n for any n larger than equals 0. So the language contains the string with a single zero, with 2 zeros, with 4 zeros, with 8 zeros, etc. Here is the pseudocode. Pseudocode says sweep from left to right and cross out every other zero. If you encounter a single zero, you're going to accept, because a single zero is really in the language. If you have an odd number of zeros, you're going to reject. So if you have an odd number of zeros that is not 1, then you're going to reject, because it cannot be a power of 2. So you're crossing out every other zero. And if you already crossed 1 0, and then you encounter another zero, but nothing else after it, you're going to reject. If neither of those happened, so you don't have a single zero and you don't have an odd number of zeros, you crossed out half of the zeros and you move back to the beginning, and you continue with from state 1 again. So it's kind of a loop. So you cross out every second zero. If you have 1 0, then you're accepting. If you have an odd number of zeros, you're rejecting. And you do it continuously. This will end because each time you're going to have less zeros. So going to end, and it's going to end either by accepting or rejecting. So this Turing machine is going to decide something, some language, and let's argue that it is deciding this language. So why does it work? Well, at every time that we go back to stage 1, we have halved the number of zeros on the tape. So if your language is in 0 to the 2 to the n, or let's say it's exactly, if your input string is 0 to the 2 to the n, after one round, it's going to be 0 to the 2 to the n minus 1 zeros, and we'll continue in every round, halving the number of zeros. At the end, we'll stay with a single zero, and with a single zero, we're going to accept. If and if it's not 0 to the 2 to the n, but anything else, then at some point we're going to half it, and at some point we're going to encounter an odd number of zeros, which is not 1, and then we're going to reject. Okay, so now brace yourself. We're going to kind of again demonstrate how using a more formal definition of a Turing machine that is as simple as this becomes very complicated. So this is the state machines for the algorithm that we've kind of described before. And we can, if we look at it enough, we can see the different stages of steps of this algorithm. So for example, this is step 2. So you're in Q0, you read a single zero, you reach Q1, and now you see the empty cell. It means that you're going to except because now you saw a single zero. And this is step one, where you're moving to the right, and then on the way back, you're turning a zero into x. So you're removing a zero. So this is a step of removing every second one. If at some point, instead of seeing two, you see one of them, you're going to, so you saw a single zero, and now instead of seeing another zero, you're seeing the empty cell, or then you're going to reject. So this is step 3. So this is the case when you see an odd number of zeros. And that's step 4, which by now I forgot what it is. We can see after we. I think this is the step where you go all the way back to the beginning of the. After you finish halving, you're going back, right? And while you go back, you're going left, and you're keeping the whatever on the tape as is. So when you read an X, you write an X, you see a 0, you write a 0. Okay, so given that we have these complicated state machines, and of course it's not very complicated, this is a very simple computation, and this was condensed, and you only have here, I don't know, 7 states. It's kind of a reasonable size, but let's see a computation path. So you start at Q0, this is your start state, and you have 4 zeros to your right. 4 zeros is, of course, 2 to the 2 zeros, which means that you're supposed to accept this. So what do? The first thing is that you move your head to the right, and you write an empty symbol to your instead of the first 0. Now you're at Q1, and you have 3 zeros to your right. You move to Q3 and erase one of the zeros. You replace it with an X. You move to Q4, and you keep the 0. This is the first edge from Q3 to Q4. It keeps the 0. You move back to Q3, and you erase the second 0 you saw, meaning that now you're at the end of your string, and you're at Q3. So now you see an empty cell, which means that you go back to Q2, and you start moving your head back all the way to Q1. After you keep on maintaining whatever you saw on the tape. So then from Q2, when you see this empty cell, you're going to move to Q1. You're going to read the X and move to the right until you reach to the 0. You're going to erase it, reach to the Q3, and then you'll end here. You'll move all the way back to Q1. Going to move one to the right. You're going to, in a movement to Q3, erase the single 0 that's still there, and stay there until you finish the X's, reach the end of the string, go back all the way to Q1 again, and then at this point, read all the X's, reach the end, and accept. So that's a computation path for this simple Turing machine. So what did we see in this video? We saw how to transform, in a sense, DFAs to Turing machine, the definition of a DFA to Turing machine. We saw how constant memory turns into unbounded memory using the tape. we saw 5 tuples turn into 7 tuples. We give more to specify, and this seems like kind of potentially small changes, but they are very major changes. A Turing machine is an entirely different beast than a DFA. In particular, we saw how easy it is to compute two languages that are definitely not regular. The X sharp X and 0 to 2 to the N, which is also not regular, as we argued in some other class. So, and that's just the beginning. We also discussed decidability versus recognizability, and we'll discuss it more.